Welcome! In today's session, we'll explore an interesting problem, special array with x elements greater than or equal to x. We'll break down the problem, analyze it step by step, and discuss the approach to solving it. Let's dive in. The problem asks us to determine if there exists a value, x, such that there are exactly x elements in the given array nums that are greater than or equal to x. If such a value exists, we return x. Otherwise, we return -1. The input is a single array of non-negative integers, where each element lies between 0 and 10,000. The output is an integer, either x or -1, depending on whether the condition is met. For instance, in the first example, the input array is 3, 5, 0, 2, 1, 4. The output for this example is 3. This is because when x is 3, there are exactly 3 elements in the array 3, 5, and 4 that are greater than or equal to 3. No other value of x satisfies this condition. In another example, if the input array is 0, 0, 0, the output is -1. Here, there is no value of x such that exactly x elements in the array are greater than or equal to x. This demonstrates that not all arrays will have a valid solution. In the third example, the input array is 0, 4, 3, 0, 4. The output in this case is 4. This is because when x is 4, there are exactly 4 elements in the array that are greater than or equal to 4. These elements are 4, 4, 3, and 4. Again, no other value of x satisfies the condition, so the output is 4. To summarize, the constraints of the problem ensure that the length of the array is between 1 and 100, and each element in the array is a non-negative integer up to 10,000. Key edge cases to consider include arrays with all zeros, single-element arrays, arrays with large values, cases where no valid x exists, and arrays containing duplicate values. For example, in a case like 3, 3, 3, 3, 3, the algorithm must handle duplicates correctly to find the value of x or determine that no valid value exists. These constraints and edge cases are critical to designing an efficient solution that works for all inputs. To tackle this problem, we need to identify a special integer x such that there are exactly x elements in the array nums that are greater than or equal to x. If no such value of x exists, we return -1. To solve this, we must evaluate all possible values of x ranging from 0 to the size of the array, denoted as n. For each x, we check whether the number of elements in nums that are greater than or equal to x equals x. This boils down to counting elements in the array that meet the condition for each potential x and verifying whether the count matches x. Our goal is to find an efficient way to perform this check for all possible candidates of x. One approach to solving this problem is by using a brute force method. The idea is straightforward. For each possible value of x from 0 to n, we count how many elements in the array are greater than or equal to x. If the count equals x for any of these values, we return that x, otherwise, we return -1. The process involves looping through every possible x and, for each one, iterating through the entire array to count elements that satisfy the condition nums I equals x. While this method is conceptually simple, it has a time complexity of n squared, due to the nested loops. This quadratic complexity makes it inefficient for larger arrays, as the runtime increases significantly with the size of the input. To improve on the brute force approach, we can use an optimized method based on sorting and binary search. By sorting the array first, we can determine the number of elements greater than or equal to any value x much more efficiently. Once the array is sorted in ascending order, the key observation is that the count of elements greater than or equal to x is equal to n index, where index is the position of the first element in the sorted array that satisfies nums, index equals x. Using this insight, we can loop through all potential values of x, find the corresponding index using binary search or linear traversal, and compute the count. If the count matches x, we return it. This method has a time complexity of n log n, due to sorting, with an additional n for the loop, making it significantly faster than the brute force method for larger inputs. An alternative optimized method involves using a frequency table to directly count the elements greater than or equal to each potential x. Instead of sorting the array, we create a frequency array where each entry represents the count of occurrences of a specific value in nums. By traversing this frequency array in reverse order, we can compute the cumulative count of elements greater than or equal to any given x.
This allows us to check whether the cumulative count equals x for any candidate value.
While this approach has a complexity of O n plus max nums, it can be faster than sorting for certain cases. However, it comes with a drawback: the memory usage depends on the largest value in the array, which can be problematic if max nums is very large. The sorting in binary search approach works well because sorting the array enables quick computation of the number of elements greater than or equal to any value x. By iterating through potential values of x and leveraging the sorted array, we systematically evaluate all candidates. This method minimizes redundant operations and strikes a good balance between efficiency and simplicity. Although sorting introduces some memory overhead, it is manageable for most input sizes. In comparison, the frequency-based approach can be faster for small values of max nums, but may encounter memory issues for larger inputs. The brute force method, while straightforward, is too slow for larger arrays due to its quadratic complexity. Overall, the sorting approach is chosen for its scalability and balanced performance in a wide range of scenarios. To solve this problem, we need to determine if there exists a number x such that exactly x elements in the array are greater than or equal to x. The first step in our approach is to sort the array in descending order. Sorting allows us to quickly analyze how many elements meet or exceed any given threshold. For example, if the input array is 3, 5, 2, 1, 4, sorting it results in 5, 4, 3, 2, 1. Once sorted, we can efficiently iterate through the array to evaluate each potential value of x. The possible values for x range from 0 to the length of the array, because the count of elements greater than or equal to x cannot exceed the number of elements in the array. For each candidate x, we check how many elements meet the condition of being greater than or equal to x. This is done by leveraging the sorted order of the array. If the array at a given index satisfies the condition, then all subsequent elements in the sorted array will as well. This makes counting straightforward, as the count can be calculated as the total number of elements minus the current index. Once we have the count of elements greater than or equal to a given x, the next step is to check if this count matches the value of x. If the condition is satisfied, we return x as the result. If not, we continue evaluating the next possible value of x. It's important to note that we iterate through all potential values of x until either a match is found or we exhaust all possibilities. If no valid x is found after evaluating all options, we return -1. Sorting plays a crucial role here because it simplifies the process of counting elements greater than or equal to any given value. Additionally, we can optimize the solution further using binary search. Instead of iterating through all potential values of x, binary search can help us identify the largest x that satisfies the condition, reducing the computational workload. To ensure correctness, we must also account for edge cases. For instance, if the array is empty, the result is -1. Similarly, if all elements are smaller than any potential x, or if the array contains repeated values like 3, 3, 3, 3, we must ensure the algorithm returns the correct result based on the problem's definition. The algorithm relies on a sorted array as its core data structure. Sorting the input array enables efficient computation of the count of elements greater than or equal to a given x. This count is derived using the index of the sorted array, making the process straightforward and efficient. The two primary operations in this algorithm are sorting and iterating. Sorting the array has a time complexity of O n log n, where n is the length of the array. Iterating over all potential values of x takes linear time, or O n. For optimization, binary search can be employed to reduce the iteration step to logarithmic time, or O log n. This optimization is especially useful for larger arrays where iterating through all potential values of x may be computationally expensive. When analyzing the overall time complexity, the sorting step dominates, resulting in a complexity of O n log n. The space complexity, on the other hand, is determined by the sorting process, which typically requires O n additional space in most implementations. The algorithm is summarized in the following pseudocode. First, the array is sorted in descending order to facilitate efficient counting. Next, we iterate through all potential values of x, ranging from 0 to n, where n is the length of the array. For each x, we determine the count of elements greater than or equal to x by iterating through the sorted array.
If the count matches x, we return x as the result.
If no such x is found after evaluating all possibilities, we return -1. The pseudocode also highlights the simplicity of the approach, where the key steps sorting, iterating, counting, and checking are performed sequentially. By leveraging the sorted order of the array, the algorithm avoids redundant calculations, ensuring efficiency. This approach ensures that we handle all scenarios, including edge cases, with clarity and correctness. This Python implementation solves the problem of finding a special integer x such that there are exactly x elements greater than or equal to x in the given list nums. ###explanation. 1. Sorting the array asterisk. The first step involves sorting nums in descending order. Sorting helps us analyze the counts of elements that meet the condition efficiently.
For example, if nums equals 3, 6, 7, 0, 2, sorting yields 7, 6, 3, 2, 0. 2. Iterating over potential values of x asterisk. We then iterate over possible values of x, ranging from 1 to the length of the array, inclusive. Each value of x represents a candidate for the special number. 3. Checking the special property asterisk. For each x, we check whether the xth largest element, i.e., nums, x1, is greater than or equal to x. This ensures there are at least x elements greater than or equal to x. Whether the next element, if it exists, is less than x or we've reached the end of the array. This ensures there are no more than x elements greater than or equal to x. 4. Returning the result asterisk. If both conditions hold for a particular x, we return x as the special number. If no such x is found after the loop, we return -1 to indicate that the array is not special. ### example walkthrough. Let's take nums equals 3, 5, 0, 6, 2 as an example. Sorting gives 6, 5, 3, 2, 0. For x equals 1, nums 0 equals 6 equals 1 and nums 1 equals 5, 1 fails. For x equals 2, nums 1 equals 5 equals 2 and nums 2 equals 3 equals 2 holds. For x equals 3, nums 2 equals 3 equals 3 and nums 3 holds. Return x equals 3. ### complexity. Sorting *O, n log n. Iteration *O, n. Overall *O, n log n. This solution is both efficient and straightforward, leveraging sorting and direct conditional checks to solve the problem. This is the Java implementation of LeetCode problem number 1608, special array with x elements greater than or equal x. The logic is identical to the Python solution, where the array is sorted, and we iterate through potential values of x to check if there are exactly x elements greater than or equal to x. Key Java-specific differences include the use of Java's arrays.sort for array sorting and explicit type declarations. In this example, we start with the array nums equals 3, 5, 0, 6, 7. The first step is to sort the array in descending order, which gives us nums equals 7, 6, 5, 3, 0. Next, we iterate through potential values of x, checking if x could be the special value. For x equals 1, we examine whether the xth element, which is nums 0 equals 7, is greater than or equal to x. Since 7 equals 1, this condition is true. However, we must also ensure that if x is less than the length of the array, the next element, nums x, is less than x. Here, the second element is nums 1 equals 6, and since 6 equals 1, the second condition fails. So, we move to the next value of x. For x equals 2, we check whether nums 1 equals 6 is greater than or equal to x. This condition holds since 6 equals 2. Again, we check the next element, nums 2 equals 5, and find that 5 equals 2, so the second condition fails again. We continue iterating through x to find a valid value. Now, for x equals 3, we check if nums 2 equals 5 is greater than or equal to x. The condition holds since 5 equals 3. Next, we verify whether the next element, nums 3 equals 3, is less than x. Here, 3 equals 3, so the second condition is true. However, this combination still doesn't satisfy the requirements for a special array. Moving to x equals 4, we check if nums 3 equals 3 is greater than or equal to 4. This condition fails because 3, 4. Since this is the case, we skip further checks for this value of x. After completing the iteration, we find that no valid x satisfies all the conditions. Therefore, the output for this example is -1. In this second example, we have the array nums equals 0, 4, 3, 0, 4. First, we sort the array in descending order, resulting in nums equals 4, 4, 3, 0, 0. We then iterate through potential values of x, starting with x equals 1. For this value, we check if nums 0 equals 4 is greater than or equal to x. This condition is true since 4 equals 1. We then verify whether the next element, nums 1 equals 4, is less than x. Since 4 equals 1, the second condition fails, so we move to the next value of x. For x equals 2, we check if nums 1 equals 4 is greater than or equal to x. This condition is true because 4 equals 2. Next, we check whether nums 2 equals 3 is less than x. Since 3 equals 2, the second condition fails again, so we proceed to x equals 3. For this value, we check if nums 2 equals 3 is greater than or equal to x. This condition holds as 3 equals 3. We then verify whether nums 3 equals 0 is less than x. Here, 0, 3, so both conditions are satisfied, and we determine that the special value is x equals 3. The final output for this example is 3. Now, let's examine another case with the array nums equals 0, 0, 0. First, we sort the array, which results in nums equals 0, 0, 0. Next, we iterate through potential values of x, starting with x equals 1. For this value, we check whether the first element, nums 0 equals 0, is greater than or equal to x. This condition fails because 0, 1. Since the first condition is not met, we skip any further checks for this value and move to x equals 2. For x equals 2, we check whether nums 1 equals 0 is greater than or equal to x. Again, this condition fails because 0, 2. Similarly, we skip additional checks and move to x equals 3. For x equals 3, we check if nums 2 equals 0 is greater than or equal to x. This condition fails once more, as 0, 3. Since no value of x satisfies the conditions, we conclude that there is no special value. The final output for this example is -1. This demonstrates that when all elements of the array are zeros, it's impossible to find a value of x such that there are at least x elements greater than or equal to x. By following this approach, sorting the array and iterating through potential values of x while checking the conditions, we can efficiently determine whether a special value exists. If no valid x is found, the function returns -1, as we've seen in this example. To analyze the time complexity of our solution, we start with the sorting step. The input array, nums, is sorted in descending order using Python's timsort algorithm, which is efficient and operates with a time complexity of O, n asterisk log, n, where n is the length of the array. Next, we iterate through potential values of x using a loop that runs up to n times. Within this loop, we check a condition that involves accessing specific elements in the array and performing comparisons. These operations are constant time, O1, for each iteration. Since the loop runs n times, the total time spent in this step is O(n). When we combine the sorting step and the iteration step, the sorting dominates because O(n asterisk log n) grows faster than O(n). Therefore, the overall time complexity of the solution is O(n asterisk log n). Now let's examine the space complexity of the solution. The sorting step is performed in place using Python's timsort algorithm, which does not require additional space proportional to the size of the array. This means the space complexity for sorting is O(1) for auxiliary variables. Additionally, the algorithm only uses a constant amount of extra space for temporary variables, such as x, and does not involve any additional data structures. As a result, the overall space complexity of the solution is O(1), making it highly space efficient. To understand the benefits of this optimized approach, let's compare it to a brute force method. In a naive solution, we would iterate over all possible values of x and count the number of elements in the array that are greater than or equal to x for each iteration. Counting elements for each x would take O(n) time, and since we repeat this process for all x, the total time complexity would be O(n) squared.
However, our optimized approach improves this significantly by first sorting the array and then leveraging the sorted order to check the conditions for all x in a single pass. This reduces the time complexity to O n asterisk log n. Notably, both the brute force and optimized solutions require only a constant amount of extra space, so the space complexity in both cases is O(1). Finally, let's break down the best, average, and worst case scenarios for our solution. In all cases, the algorithm begins by sorting the array, which dominates the time complexity. Therefore, the best case time complexity is O n asterisk log n, as sorting is always required. The average case complexity remains the same, O n asterisk log n, because the sorting step does not change. Similarly, the worst case complexity also stays O n asterisk log n, as the sorting step still dictates the overall performance. From a mathematical perspective, the sorting step's O n asterisk log n time complexity outweighs the O n contributed by the iteration step, which is asymptotically smaller. On the space side, the algorithm relies only on in-place sorting and constant auxiliary variables, ensuring an overall space complexity of O(1) across all scenarios. When solving this problem, there are a few common mistakes to watch out for. First, it's easy to misunderstand the key condition. Remember, the value of x must match the number of elements in the array that are greater than or equal to x. A common error is to count elements strictly greater than x, which doesn't meet the problem's requirements. Another pitfall is mishandling duplicates. Duplicate values can skew the count of elements greater than or equal to x, especially if you're iterating through a sorted array without careful consideration. Additionally, edge cases can trip you up. For instance, arrays that are empty, contain all identical elements, or have numbers smaller than any valid x need special attention. It's critical to ensure your solution handles these cases and doesn't return invalid results, such as a positive number when no valid x exists. Finally, inefficient solutions like recalculating counts repeatedly in a brute force manner can lead to unnecessary complexity. Optimized methods like sorting or binary search are better suited for this problem. Also, don't ignore negative numbers. Assuming only positive integers can lead to issues, since x can be any integer, including negative values. Now, let's focus on insights that are especially useful during interviews. A key pattern to recognize is that sorting the array makes it much more efficient to determine how many elements are greater than or equal to any potential x. With sorting, the problem complexity can be reduced to O n log n, which is often acceptable in interviews. Clarity in your logic is also crucial. Sorting followed by a single pass to validate potential x values is not only efficient but also straightforward to explain. Make sure to demonstrate your awareness of edge cases, such as handling empty arrays or arrays consisting only of zeros. Bringing these up unprompted can show the interviewer that you're detail-oriented. Additionally, discussing trade-offs is important. While sorting-based solutions are typically optimal, you could also mention alternative approaches, such as using hash maps to track frequencies. These have their own advantages, like avoiding sorting, though they may come with a higher space complexity. Being able to discuss these trade-offs thoughtfully can leave a strong impression. This problem is closely related to other array-based challenges, which can help you deepen your understanding of similar patterns. For example, LeetCode 275, the h-index 2 problem, also involves counting elements greater than or equal to a threshold, but it specifically works with a sorted array. Similarly, LeetCode 274, the h-index problem, introduces a variation of this concept using citation counts. Another interesting problem to explore is LeetCode 1385, which involves comparing elements between two arrays while satisfying certain constraints. It's a great exercise in array manipulation and constraint-based logic. Lastly, LeetCode 2389, which focuses on finding the longest subsequence with a limited sum, combines sorting and binary search to handle array-based constraints. These problems often require similar techniques, such as sorting or iterating through arrays efficiently, so practicing them can provide valuable insights and prepare you for variations you might encounter in interviews. There are several alternative approaches to solving this problem, each with its own trade-offs. One of the most common methods is to sort the array in descending order and then iterate through it to find the first valid x where the condition holds. This approach has a time complexity of O n log n due to sorting. While it's straightforward to implement and explain, it does require modifying the input array. Another approach involves using a hash map to count the frequency of elements. With this data, you can iterate through possible x values and check the condition. This method avoids sorting, achieving O(n) time complexity for frequency calculation, but at the cost of increased space complexity. Finally, there's the brute force method, where you calculate the count of elements greater than or equal to x for each possible x. While this approach is simple and helps in understanding the problem, it's highly inefficient with a time complexity of O(n squared). Each of these methods has its place, depending on the constraints and requirements of the problem, and understanding these trade-offs is key to choosing the right one. Great job! We've successfully analyzed and solved the problem. Remember the importance of understanding the problem thoroughly and leveraging sorting for efficiency. See you in the next session. Stay curious and keep practicing. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!